And I would like to start with thanking the organizers for giving me this opportunity to speak. I have put together a new set of slides that I was quite excited to make, so I hope you like it. If the microphone is on. Maybe, yeah, can you hear me? Should I speak louder?
Maybe move the microphone further out. Yeah.
I don't know what to do, Tom. Like this? Okay. Yeah. Okay. I'll be loud. Okay. And the people in the back, if you don't hear me, you can come forward. So I was thinking to try and make a connection between strip stars and black holes. And actually, I do really believe there is a connection. Yeah. So it's not that I'm making something contrived now. And I wanted to start with a take-home message, which I hope by the end of the day I have convinced you, or you start to believe that we can actually use envelope strip stars to help reduce large uncertainties that we have in binary evolution models now. And it's quite exciting, so I think we can do quite a lot of things in the future. Let's start with a little bit of background. Just so that we're all on the same page, I'm going to have quite some technical stuff in this presentation, so let's start less technical. What is actually a strip star? Yeah. This is a binary product. It starts with two stars in a binary. Here we have a double main sequence star. They burn hydrogen in the center. And we're going to look at this Hertzsprung-Russell diagram here, which have effective temperature going in the reverse direction on the x-axis and luminosity on the y-axis. During the main sequence, we're going to look at the donor star, the most massive star. It evolves a little bit. This is a 12 solar mass star. It becomes a slightly more luminous, slightly cooler. After the main sequence, the star has depleted hydrogen in the center. This helium core contracts, ignites hydrogen in a shell around the helium core. And this causes the star to expand drastically. This expansion makes the star fill its Roche lobe. It has a binary companion, so the Roche lobe is filled, and material starts flowing from one star to the other. We call this mass transfer. Mass transfer looks like this in this specific MESA model that I made. They can look slightly different. I have a few examples of mass transfer. What is left now afterwards is just this exposed helium core with a little bit of hydrogen left, and this star contracts to high temperatures. It spends most of the helium core burning lifetime over here at like 80,000 Kelvin, and eventually this star, it will explode, 4 solar mass strip star, as a hydrogen poor supernova. I started to doubt at Adam's presentation yesterday whether 4 solar mass helium stars should explode or not, so got slightly nervous there. But anyway, it will be hydrogen poor, and in comparison to a single stellar counterpart, which would be a hydrogen-rich supernova, we would have completely different progenitors and completely different supernovas. So you can have some change in the evolution thanks to this envelope stripping. Now, I wanted to show some interior structure, which I think is going to be important. So here, this diagram is showing a cartoonish version of composition on the vertical axis and mass coordinate inside of the star on the horizontal axis. The center is at 0, and the surface is where it says surface there. So during the main sequence, the star has a convective core that recedes in mass coordinate, leaving a composition gradient on the outside of this helium-rich layer. And this composition gradient, it looks like this X shape. So during mass transfer, we remove the flat composition part, the outer envelope. And what is left, according to models, is something that it stops somewhere in the middle of this composition gradient. So what this suggests is that the helium star, the strip star, is not a pure helium star, but it actually has a little bit of hydrogen, which means that it can do hydrogen shell burning, and it also is a little bit fluffier, so it's a little bit cooler than a pure helium star. And it's also a little bit more luminous, no? It has hydrogen shell burning. So, with that context as a background, let's go through the outline that I wanted to talk about today. First, that strip stars, they matter for black holes. Then I think we will go into the physics that we can learn from individual systems. You remember what Tom said yesterday? I thought it was beautiful phrasing, that you can learn a lot from just individual systems, and this is also where we are at this point in strip star observations. We don't have large populations yet, but if we were to have large populations, this is what we're going to reach finally in the presentation. So let's start with the strip stars that matter for black holes. And I would like to start with pointing out, I think that you have all seen Selma's pie chart, that a third of massive stars are expected to go through envelope stripping, which means that a lot of the progenitors of black holes are strip stars. And even if this says a third of them, I mean a third is a sizable fraction, so I would even dare to claim that you cannot ignore the strip stars. To better understand the black hole, you need to understand the progenitor. If the progenitor is a strip star, that's what you get. So that's a reason. Now, of course, you're familiar with the evolutionary sequence that reaches the merger of two compact objects. This is the isolated, I would call it classical or standard isolated binary evolution channel that leads to binary black hole mergers. And in this case, we have two strip stars here. You may see that they are called somewhat different depending on who made the graphics. Here they are called helium stars, sometimes they are called Wolf-Rayet stars, I would doubt that. And sometimes they are called strip stars, when I make it, they are called strip stars. And then I want to point out that here we have the black holes. Yes, it's actually rather close to the black holes. It's just one little core collapse in between. And so, another thing is that if we're going to measure stuff here in the merger, then you have to go through a lot of different steps, and if there's large uncertainties in these steps, maybe we can try and narrow it down from the other direction first. And the strip star is the first binary product. If we don't consider mass transferring binaries a binary product, maybe it is a binary product also. That's maybe a future project. So I think we can ask some interesting questions when we look at this diagram. Which could be, for example, what strip stars can create black holes? How do the core collapse and the potential supernova then impact the system? How does envelope stripping affect the orbit? And maybe do tides matter at all? And there's lots of fun things you can work with if you go to the strip stars. So let's start with the first question, just so that we're all very clear that there is a connection. This diagram is 1D supernova models that were created by Fabian Schneider. And he plots here the carbon-oxygen core mass on the x-axis, but I took the liberty to put the strip star mass on top. And you can see that there is an island of inexplodability, what's the name, no, Adam? Here around 7 solar mass strip stars. And depending a little bit on the 1D models, this island moves around a bit. It's somewhere between 6 and 9 usually in 1D. With David Vartanian, we had a nice project where we make 2D models in 2021. And so here what David is showing is the time after the bounce during the core collapse. So we gave him a bunch of models. The solid lines are strip stars. And the radius, as the radius evolves, so an exploding model would shoot up like that, while the failed supernovae maybe go like this. And the ones that we have there actually are the strip stars with 5.5 and 6.5 solar mass, something like this. So I would say we're not yet, how I read this, is that we're not yet super sure exactly what strip star is going to do what black hole, but they could make black holes. I think we're kind of agreeing on that could happen. And I think Kishele has some some exciting stuff happening after me, so please, that's going to be interesting. There is potentially some indirect proof that I thought I could mention. This is a system called SS433. It's called a microquasar, but really it's just a mass transferring binary, where you have a black hole of 4 solar masses. If you want to say that's not a black hole, I'm fine with that, but I thought it's a black hole. And a 12 solar mass donor star. The orbit is short, it's 13 days. So for that orbit to be so short, you must have had interaction before, or a very favorable black hole kick, I would say. There is another example. This is quiescent, completely different from a wavelength point of view, flux point of view. This is a quiescent black hole that Tomer found, where the black hole has 10 solar mass and the star has 25. And this is also a short period binary and circular. So I would even dare to claim that this is so tight that the progenitors of the black hole probably went through mass transfer. Yeah, Johan, you have a question?
What are these processes will affect the final state of the black holes that form these processes?
Oh, yes.
There's many things going on, right? You have the tides, the orbit, the mass.
I would say tides can do it. This is probably a little bit wide to do tidal locking for these objects. Lin Hao is nodding, so I feel confident. I could also say maybe angular momentum transport inside of the star can change and affect. So that would be interesting as well. But yeah, actually spin of the black hole, future hobby of mine, but I haven't gotten sufficiently far yet. Okay, is that enough? Yeah, okay. I think where we are certain is that we know that strip stars can become neutron stars. So because we know that there are BE X-ray binaries, let's remind what is a BE star or how you can create a BE star through binary interaction. You do mass transfer, the accretor star spins up, starts to shed this disk because it rotates so rapidly. Then you have a core collapse, and the neutron star can start to plunge through this BE star disk. And that means that if you have neutron star BE X-ray binary, it's probably the neutron star was a strip star once. And I thought that there was some really nice work by Ruggero Valli this year where he shows that we're looking here at period versus eccentricity of BE X-ray binaries. That's the markers. And there's 2 groups. One group that shows almost no eccentricity, consistent with almost 0 kick. And one group with larger eccentricity, which has supposedly a small kick during the supernova. So interesting stuff that hopefully we see a future follow-up on. So let's move to what I think we can learn from the individual systems. We're starting to observe strip stars. And it depends a little bit on the definition of a strip star, what you think when we started to do this. But I want to highlight that in the strip star mass spectrum, there is roughly a boundary of about 2.5 solar mass, where above which you could make core collapse and neutron stars and black holes. And I will focus on those today. This is my biased opinions of what we have seen or not seen. Here we're looking at the strip star mass compared to the companion star mass. The blue dots are actually Wolf-Rayet star binaries, Wolf-Rayet plus O star binaries. So some of them are maybe a little bit questionable, like this one here, given that an O star typically does not have 7 solar masses. So we are not so sure here with the masses all the time. Also, Wolf-Rayet stars can be formed through wind, so it's not so clear all the time that the Wolf-Rayet star in this case are the products of a binary, but the O stars are rotating, which was encouraging for Mike Shara. I am responsible for the purple stars, and I will show you a little bit more about that. And that's also the actual mass estimates for the companion stars come from a PhD student, Alex Laroche. The pink ones are fluffy, cooler objects that are thought to be perhaps partially stripped, and I will also show a little bit more about that. So, to begin with, from a theory side, where we are today and have been for several decades is that our evolutionary models look roughly the same. This is the first model made by Kippenhahn and Weigert in '67. And here I thought this was, just because it's beautiful, by Jaime Villaseñor, a model made in 2023. So if you look at these strip star tracks, we can definitely recognize similarities. There has not been super much differences. Maybe you can see that they avoided a bit the Roche-Lobe overflow here in '67, but honestly, the guess was not so bad. The Roche-Lobe overflow can look a little bit different. For example, here is a model from stars made by McClelland and Eldridge, and they have the Roche-Lobe overflow here. It's a little bit hard to see that as a Roche-Lobe overflow, but that's what it is. Otherwise, they look rather similar. You can see slightly different location of the strip star, helium core burning, and the turnaround. And this is wind-related and something that the Bashish is going to talk a bit about tomorrow also. So how can we understand whether these evolutionary models are actually an accurate representation of what nature does? No? So now, since we have some observations of strip stars, I'm not going to show you how we found this, but this is a set of helium stars that we discovered in the Large Magellanic Cloud. There is also a set in the Small Magellanic Cloud, but this is from the Large Magellanic Cloud. And here I have overplotted the properties that we determined for these objects in the Hertzsprung-Russell diagram, so effective temperature and volumetric luminosity. Now, you can measure, from a spectrum, you can measure easily effective temperature, surface gravity, and surface composition. This is stuff that comes out from spectroscopy. If you know the distance, you can get a decent estimate for the luminosity as well. So if we compare here with another type of diagram, this has sometimes been referred to as the spectroscopic Hertzsprung-Russell diagram, but it's really on the y-axis just a combination of effective temperature and surface gravity. And do you want to chime in here?
Can you do this measurement if you have strong wind?
That depends on how strong wind. You can always do something. Yes. And so now let's look. You can see that the figures look rather similar, but there is especially one star that moved a little bit. No, it's number 5, and so number 5 is not a good representation. It's not well represented by these models, is what that means. So, for example, if you were to use these models to infer an evolutionary mass of star 5, this would not be accurate. Star 5 happens to have lower surface gravity than what these models predict. It's a question why, yeah, but it has. Okay, so I would say for the other stars, what this shows is that actually we were not that off when it came to effective temperature, volumetric luminosity, surface gravity. That looks rather decent. We have recently started to do also orbital solutions for the strip stars. This is work that I handed over to Alex Laroche, a PhD student at U Toronto, and he has used he developed quite a bit of code to accurately measure the radial velocities. We don't have to go into detail on how to do that, but found several orbits, and what he found was that the orbits actually cover a wide span, from hours to year-long orbits. So this is some orbits. You can see we didn't get orbits for everything, among them star 5, yeah? But there are some other orbits and some constraint for the eccentricity. Everything is consistent with 0. Something we found was interesting that Alex did here was to compare with what is the surface hydrogen mass fraction of these objects. And you can see that the ones with an orbit have hydrogen. And they have about, on average, a hydrogen mass fraction of 0.35. And this, we think, is, what that means, we think, is that this is the boundary between core and envelope inside of the star. It happens around 0.35 mass fraction in this rough metallicity. Probably this is metallicity dependence as well, but there is a boundary. Evolutionary models, sorry that this is not very clear, but they predict something like between 0.3, 0.4 for this mass range. And what that suggests is that actually, yes, there is a little bit of hydrogen of that chemical gradient left. And so now what these orbits and that chemical gradient does to our understanding of the mass transfer and the evolution is something that Dan is going to talk about tomorrow. So this is quite exciting stuff, and I will not spoil her presentation. But what Alex could get out of the orbits as well is companion masses. So this is some distribution because they are single-line spectroscopic binaries. So we use a random inclination distribution, and then you can pull out a best fit mass for the companion and then an error range. And what you can see is that the companions have low mass, typically between 0.8 and 4 solar masses. And this in itself is also quite useful for figuring out how the binary evolves, etc. But we haven't gone very deep into that specific aspect yet. So moving away from our survey, I wanted to highlight another thing that I think has theory is moving in this direction now. It's becoming more clear that our theoretical models predict that at low metallicity, massive stars, they can burn helium as blue supergiants. And this affects the envelope stripping process. Here is a model from Jakob Klensky of a 30 solar mass star at solar metallicity. It goes through the mass transfer, and then you get this hot stripped star over there. But at low metallicity, this does not happen. No? So instead, it can do nuclear timescale mass transfer. So it just stays mass transferring until death. Or you do a little bit of partial stripping and bounce in and out of mass transfer and stay rather cool like this. So this prediction means that we now, for that mass range and metallicity range, there can be lower surface gravity objects, fluffier objects, and objects with a little bit less helium enrichment. And this lower helium enrichment is because for the star to burn helium as a blue supergiant, it needs to develop a thick convective layer inside of the star, details, but important for what happens to the evolution of the star. Okay, so this prediction, and Jakob can tell me if he doesn't see it this way, but I think is that we have long-lived, less stripped massive stars at low metallicity. They could exist. And there was some observations by Varsha Ramachandran in the SMC, I believe. Maybe it's a mixture of objects here, actually. Maybe it's not just SMC. And at a little bit lower luminosities, but these 4 binaries, 4 stars, they seem to have high nitrogen enrichment, which could come from this central CNO cycle during the main sequence, and moderate helium enrichment, fluffier objects. So it could be a counterpart to this. Yes. The masses are perhaps a little bit low, the luminosity is a little bit low for that mass range, so we really, probably, this is a nice direction where we can do some tests now, observationally, I would say. SMC, there is a survey called Bloom. Perhaps there is some directions you can go in that survey. Just look at that. Now, so let me finish up with some population discussion. So if we're going to move towards a population from these handful of objects, okay, 10-ish objects, we're going to need to do something. Thank you, Ilya. So Bethany Ludwig, who was a PhD student at U Toronto, now a postdoc at KU Leuven, she did careful photometry reduction of the UV images of the Magellanic Clouds. And one thing that you can see here that shows why you need careful photometry reduction, it's very annoying, is that sometimes aperture photometry, captures more than one source. So, yeah, it's very, very annoying. But, so she managed to identify here, okay, I haven't shown you the color magnitude diagrams yet, but she managed to identify several hundreds new candidates. So then you may ask, is that in line with what we expected in the Magellanic Clouds? Should we have hundreds of new candidates? So we did a comparison. My previous undergrad, Beryl, performed some population synthesis and did some estimates that the LMC should contain 6,000 and the SMC 1,600 in the specific mass range. And so that seems like we're totally in line, but actually the specific technique that we used is not sensitive to all of these. And this is work by Lisa Blomberg at Caltech, when she went through a survey completeness for this survey and identified that the sample of Bethany is sensitive to only about 10% of the strip stars. But luckily, and this is a little bit complicated plot, but the blue here is the blue is the model, and the dashed one is the survey of Bethany, and it looks like it's completely off here at the low, high magnitudes, but actually in the mass range that I care most about, we're totally fine. Yeah? So that's nice. So now, why would we need more stripped stars? We currently have individual systems, and what we could do is we can do some benchmarking of evolutionary models, find the core envelope boundary, and test some mass transfer stuff, moving to a large population. What I think is going to happen if we do that is we can do things that explores if envelope stripping is common. Is it as common as we think? What's the most common envelope stripping mechanism? Is it mass transfer? Is it common envelope? How conservative is mass transfer? Can we measure that perhaps? Under what conditions? And is there actually a critical mass ratio? Does that exist? I mean, we have a lot of theoretical concepts that we actually may benefit from having a bit more tests on. So I thought we should make a new population model. I felt a need for a new population model because I felt the models that we had, they could not be sufficiently flexible in changing the evolutionary models. And also, we want to represent strip stars with binary evolution models rather than pure helium star models. So I'm not going to go through the initial conditions. I think this one is a much better diagram. So beautiful graphics here from Giuliano. I have my code is a tent and not a fortification. Simple code. On the border of forest of unnamed codes towards the meta direction. And I'm working on the name. I have several suggestions. How a prediction looks like at the moment. Something like this. So this is a Hertzsprung-Russell diagram. We see strip stars and their companions. Strip stars are colored by their mass. Companions are less important, so they are gray. And if we focus on strip stars more massive than 2.5 solar masses, we can see here temperature, radius, hydrogen mass fraction, and mass distributions. We find that strip stars are hot. 98% of these have higher temperature than 30,000 Kelvin and should be hotter than the main sequence. They are small, less than 2 solar radii, and hydrogen poor. Now that's of course a product of what evolutionary models I put inside, so if we change those, we maybe get a different distribution. Yes, and let's note that the bolometric luminosity needs to be higher than about 10 to the 3.7 or something for you to have explodable strip stars. That's the regime. We can put it inside of this diagram with the strip star mass and the companion mass. And we can see a few things, a few structures. On the top here, we have the conservative mass transfer. And this is the only place where you get O-type companions for these intermediate mass strip stars. These are the only ones that are sufficiently massive. In this regime here, in my model, we don't have any accretion for those ones. So that's Hertzsprung gap mass transfer and mass transfer with a stripped companion or a compact companion. And in fact, if we look at the different types of companions, maybe it's slightly optimistic with the neutron star companions here, but we can discuss that. The large majority of stripped stars, they orbit main sequence stars. I guess we already guessed that. Yeah. And if what I want to point out is that this diagram, actually, if it shows structures, if we manage to populate that observationally, I think we can get some information on, for example, mass transfer efficiency and how these different interactions actually happen. So we had that observational diagram now, a little bit small amount of data. So I can see that we can populate a bit more here, so we can actually make a more fair comparison. I have some period distribution to finish with. This is a period distribution, and it is only for the more the explodable strip stars. And there's a structure. The structure comes from the way we have treated the envelope stripping. So the short period here is common envelope ejection, about 20%, and the longer periods, between 10 and several thousand days, is the mass transfer. And then we can do, yeah. So to actually compare with data here, this is just, yeah, so that we can conclude that we don't have enough data. And I think that I'm over time, so I'm going to skip this. Okay, just to point out that UVEX is going to help us in the future and covers this beautiful spectral line that the Bashish will show you. But let's finish with the summary that I think strip stars are pretty clearly progenitors of black holes. We should care about them. And with these individual systems, I think we can learn about the physics of the previous interaction and help narrow down a little bit our enormous uncertainties. And I think a population is needed. And I think with the population we can learn much more. It's a little bit, I mean, not the same, but like the gravitational wave community a few years back, where with just a few events, moving to where we are today is really beautiful to see what you have learned about the physics. And I think this, I mean, it's just a star, but it would be interesting to, and I think we can learn a lot from moving to a larger population. So thank you so much, and for the extra 2 minutes also. So,
wow, we have a lot of questions. All right.
Thank you. You have a very nice talk. I'm thinking about if you can do a spectroscopy for some of these strip stars, can you actually measure their rotation rates?
Yes, you can. Actually, in fact, I had an undergraduate student who did this in 2021, but Ashley now, she has started aerospace engineering grad school. So I'm hoping that Andre is going to do this. My other PhD student is not here.
Thanks, but there's a system, I think it's 6-hour orbit that you were showing, the stars 3, or I don't remember, but did you measure that? Or?
Yeah,
I think that's possibly interesting for tidal interactions. Like, yeah, so.
Yes, orbits are very precise, masses are less precise. Orbits were certain.
Yeah, but the rotation of that star.
What happens, unfortunately, when you have such a fast-moving object is that you need to take very short exposures so that you don't smear your spectral lines. And that is a faint source, so I wouldn't say that I'm certain about it yet, but it looks a little bit smeared to me.
Okay, thanks, great.
Sorry, we're just going to try to go to people who haven't asked too many questions yet.
Thanks for the amazing talk. So in the observed sample of strip stars, their companion masses seemed lower than what you were predicting in the population. Is that like a selection effect that it's hard to find strip stars if the other star is a lot more massive and bright?
Yeah, okay, yes. Good point, Niv. Let me put up that thing. Okay, so it's a tent, my population model. So the masses here, we need to look a little bit closer. It goes back to also your initial mass ratio distribution, which I truncated at 0.1. So if we don't do that, maybe we can have a little bit more lower mass. Also, you can see all of my neutron stars are poorly represented in mass. And, yeah, so you can do a slightly better job. Maybe you need to throw in some black holes here. Could be. But yes, lots of stuff. Mm-hmm.
So that's my question. Your population so far has no black hole companions to it, it looked like from your pie chart. Do you believe that yet, or are you still working on understanding that?
I mean, implemented something very simplistic for the stripped star to companion or compact object relation. I feel more confident on the white dwarf direction, to be clear, to be honest. I got very into the stripped star white dwarf creation scenario, and I know that we're not in that community right now, so I'm really happy to learn how could I improve the black hole mass mapping and what neutron stars to put and stuff. So no, I don't really believe it.
Ylva, thank you for the amazing talk. So first a comment, when I put this forest of unnamed codes, I was exactly thinking to your work, so I'm happy you put that here. And then a question. So actually, we know that there are also stripped stars at low masses, no? Like, for example, the subdwarf. So do you think that these kind of models, or anyway, do you think that you can make connection between the two populations in terms of prediction and models, or they are too different in terms of mass regime to really?
This is a good question. So there is lower mass stripped stars. Subdwarfs is a quite large population. Subdwarfs are clearly binary products. And a fraction of subdwarfs come from envelope stripping, another fraction probably comes from merger or so. Subdwarfs are a little bit more complicated because a large amount of them can come from low mass stellar evolution and degenerate core stuff. Mm-hmm. And I'm just not sufficiently good at low mass stellar evolution yet, but I'll put it in, and then I can make a better comparison. But yeah, and I also left out the lower mass objects because I know we have several talks on those, and I didn't want. I thought that then I can focus on the more massive ones.
Hi, Ylva. Thanks for a great talk. I wanted to ask if you have candidates for binaries with 2 strip stars and a large sample from beta near. Would you be able to see them?
Thank you. What a wonderful question. So my population model predicts that there. Here you can see. Okay, here you can see the colored dots are the strip stars that come from the initially most massive star, and the colored dots with a little circle come from the second star in the system. And in about 0.5% of the cases, you create a double strip star. This is just a theory prediction, and we'll need to look a little bit closer into this very, very rare channel. But it agreed quite well. Actually, I was talking with Manos Zapartas, who's been running some Poseidon models, and we had similar rates. So I was quite encouraged. We have not yet seen anything like that, but I know that there is a double subdwarf, and that has been quite encouraging. So I hope in the future, yeah, it's just very rare.
Thank you for a really interesting talk. I have a question about your theory model, the code, and if you included tides, what type of tides, and do you see this feature, the feature that you said, oh, I see 2 different formation scenarios, do you also maybe tying it to, as a signature to tides of the separation, which is actually similar to binary stars and even triples?
Thank you, Smadar. That is pointing out, I would say, a flaw in my code. I don't yet have tides, but indeed, this short period ones, also what Linha was pointing out, if you have less than a day, maybe, we probably could have some tidal interaction that could be quite interesting and lead to further mass transfer, maybe even during the helium core burning. It can be very fun, but it's not yet implemented, but I'll work on that.
Thank you. Wonderful. So much material to work on. Here's my question. As we move towards population observations to have to compare to, what's your opinion about modeling the selection effects? Because I mean, I understand from the observations they're not easy to find and characterize, and if we're going to make direct comparisons, that will have to enter. Do we have a good hope for modeling the selection effects?
Thank you for that question. Selection effects is not my favorite part of the work, but I am lucky to work with some great people who, especially Lisa and Karim, helped a lot with the selection effect calculation, so we could actually do a population comparison with this specific
Fantastic.
sample.
Yeah.
Now, depending on how you detect strip stars, you will have to do different models for that. Yeah. But, I mean, I'm feeling confident in us as community. I think there is lots of expertise in this, and I know what I don't know. So that would be great to get some help with.
Yep.
Hi. Could you maybe say a little more about the star 5 and the stars where you don't get an orbit? So I guess you don't get an orbit because you think they are not binaries, or because you think the companions are too low mass? And why, like, how does that fit in with the low hydrogen?
Yep. Good question. So Alex has various work to do because we were just hoping this would be easy. You know, everything is binary. We just publish the orbits, and voila, they match mass transfer and common envelope predictions. Doesn't seem to be the case. And we have here these 3 stars that, honestly, they don't seem to move very much. It could be consistent with an orbit that is longer than, say, 1,000 days, and according to the prediction, that's still okay, but it's very long. And I would have liked to see a little bit more of a trend in the radial velocity. They also happen to be hydrogen-free, so I don't dare to say too much. Ilya has already grilled me a little bit on this. You forgot? Huh? I think I'm going to leave it for Alex to publish in a year or so. Yeah, he's going to publish the orbits first.
Ylva, you might say that I've already asked this question, so I apologize, but star 5 in particular, right, is your puffy star, right, because it had a low log G for its luminosity and temperature relative to your models. And so does it mean that it's actually a post-helium main sequence star? So it's already expanding on the helium cross-parent gap? Is that the idea?
I think so, but that's a good question. I checked the contraction phase, but not so much the expansion phase. I'm going to have to check the expansion phase. Yeah, that's a good point. I know. I will have to come back to you.
Okay, I think unless there is one final very urgent question, we should probably move on. So thanks again very much, Ylva.